So hello everyone. Today we are going to uh, I am going to present you how a SAP-1 circuit works. So the SAP-1, or as simple as possible one, is a fundamental 4-bit computer model designed to introduce basic computer architecture concept. So in this one, we'll explain the main components first of the SAP-1 and simulate how it executes the given program. So first is the program counter. The program counter is responsible for uh, this one above here. It is responsible for holding the memory address of the next instructions to be executed. So it increments automatically after each clock cycle, ensuring sequential execution of instructions that stores in memory. If required, it can be reset to start the program from the beginning. So next is the MAR, or the memory address register. It's here. So uh, it temporarily stores the address provided by the program counter. It serves as a bridge between the program counter and the ROM, where the program instructions are stored. By isolating the address from the program counter, the MAR ensures a smooth fetching of instructions. Next is the ROM. The ROM is presented here, and this is the main chip, this one, the huge one. Uh, It is where the program is stored in a hexadecimal format. For the given program, the instructions include operations like loading a value, or the LDA, adding a add button, add instruction or add state, subtracting state, and outputting the data, and halting the data. So each instruction has a specific opcode stored in the ROM. And next is the instruction register, or the IR. So here it is in the bottom. Oops. So it fetches the instructions from the ROM via memory register. It splits the instruction into opcode and operand. So the opcode defines the operation to be performed, while the operand specifies the data or memory address. Next is the controller sequencer, just below the instruction register. It manages and controls the signal for the entire system. It ensures that all components work synchronously according to the fetched instructions. For example, it enables loading of data into register, or the activation of the arithmetic logic unit, or ALU. Then next is the accumulator, which is here at the top, accumulator A. So this one uh, is for arithmetic and logic operations. It temporarily stores the value uh, of the result of operations performed by the ALU. For instance, when adding or subtracting numbers, the result is stored here before being moved to the output register. Then the B register, just below the accumulator, is used for the second operand of arithmetic operations. So when there's already a value that gonna be added or subtracted, uh, the value from the B register is sent to the ALU to be added or subtracted from the value of accumulator. Then the ALU, which is stated before, is the addition and subtraction. So it is the input from accumulator and B register, then it solves them and send the result back to the accumulator. Then next is the output register, which will output the display of the total result here, and gonna be shown in the 7th segment. And next is the clock, which synchronizes all the operations within the circuit. So let's start. Let's start from the operation here. So you can see it's turned off currently. So let's turn it on, which will connect to a ground. Then, as you can see, the program counter is 000, which will be fetched by MAR. So if you click it, it's already there. Then, uh, the instruction register decodes the instruction and the value at memory address 0, which is gonna be 5. So let's start. So as you can see, it's already in 8 because at the ROM is already in 08 at 00. Let's see. You can see that. We turn on low and the accumulator is 000. And then let's send, you can see the program counter incremented by 1. And then mar will take that and see. As mar, as program counter as mar take the value of program counter, which is 000 earlier, um, mar then is now gonna be in instruction register, as you can see. So if you look at the instruction register, uh, the first four values will be for the controller sequencer, while the first four digit is based on MAR. So if you can see, we are still in the load or LDA, which is 000. If we are on 1, which is 0010, is going to be add. And if we're going to be subtract, this is 001, 1110. And lastly is 1111, which is the halt. Okay, so let's start. You can see as the ROM is taken, the accumulator takes that ROM, it says there, and then the accumulator is presented with 5. So let's go to our next one, which is 11 here. So let's go. So the counter is still in 0, which is loading. So we have to 5 plus 11 minus 6. So that's 10. So we already added 5 plus 11, uh, which is 19 here. As you can see, just 19. We're still not in 11. So let's load and see. The program counter incremented again, which mar will take. There you go. See? So now we are at 0001, which is add. So let's send the 11 to the B register. So the value 11 now is in B register. So the process is like basically this. The mar takes the program counter and the program counter increments. Mar then takes the value of uh, ROM, and then ROM says a instruction register, and then the controller sequencer is based here. So as you can see, 0001 is the same as here, and then the first one here is the mar. So you can see 1001. Then let's solve it. So 5 plus 11, it will store the sum here in accumulator A. So let's go. So you can see it added into 16. So you can see the ROM is 10001, 10011. So let's go for subtraction. So we need to increment this into, okay, 6. So you can see it's 0000, 0110. So we have the program counter here. So the instruction register now decodes the instruction. The value of the memory is loaded into the B register. So as you can see, we have 11 and 6, 16. So that resulted in 6. So let's try it again. Now it's 10. So 16 minus 6 is 10 now. And then we're in the output, which we are going to display it here. The value of 10 will be set in output register, then it's gonna have an output. So let's go again. EEE, sorry, 11 to A, okay, some by 6. Then we're going to display at the next click EEE, which is here, stored in the value of the ROM. Now it is registered. So we have output in EEE. As you can see, EEE, the value is now registered in output. Then the last one, as you can see, is 111, which is output. And the last is FFF, as you can see, this one, which results in halting the whole operations that even if you click the controller, it doesn't do anything. It's just stop intent always. You can see FFF, which is 111, nothing's happening anymore. So that's how a SAP program works. So it increments 4 by 4 now, as you can see. So SAP-1 is an excellent model for understanding uh, how the computer system executes instructions step by step by breaking down its component and simulating a program. Uh, this is an insight for the foundation of computer architecture and how they are built upon in more advanced systems. So that's all. Thank you for watching. Have a great day.